Okay, so get this. Today's deep dive takes us into the world of AI, but
Yeah.
specifically how machines are learning to understand things in order, just like we do when we read a sentence or follow a recipe.
Yeah.
We're talking sequence to sequence modeling, so
And what's really cool is that, like, it's not limited to just language. We're
yeah,
talking about predicting stock prices, understanding protein folding. This stuff is everywhere.
it really is. And to help us break it all down, we are diving deep into a chapter from Deep Learning with PyTorch Step by Step.
Great book.
Oh, yeah. And trust me, this isn't some surface level skim. We're going to break down how these models actually work.
Yeah, we'll explore, like, the key players,
Yeah.
encoders, decoders, the
Exactly.
game-changing attention mechanisms. And this is a big one, something called positional encoding.
Because timing is everything. It's like that friend who's always late. You can't just pretend it doesn't matter.
Yeah.
But before we get ahead of ourselves, let's start with the basics.
Okay, so imagine teaching a machine to find the corners of a square, right? You give the coordinates for two corners.
And the big question is, can it figure out where the other two corners should be?
Exactly. That, in a nutshell, is a sequence-to-sequence problem. The machine needs to understand that the order of those corners matters.
Okay, that makes sense. But how do we even begin to teach a machine to think that way?
Well, that's where encoders and decoders come in there. They're like the heart of this whole operation.
Okay, so walk me through it. What do these encoders and decoders actually do?
So think of the encoder as like the note taker. It takes the input sequence in our example, the first two corners of the square, and it kind of boils it down to the essential information, a hidden state, like summarizing a whole chapter into a few bullet points.
So it's picking out the key takeaways. Then what? What does the decoder do with that information?
Right, so then the decoder steps in as the storyteller. It takes those bullet points, the hidden state, and uses them to, reconstruct the whole story, or in our case, predict the remaining corners of the square.
Clever. But I have to imagine it gets complicated, right? Like what happens when the sequence is super long? Can the model handle that much information?
Yeah, that's the catch. Those early, more basic encoder-decoder models really struggled with longer sequences. That single hidden state was like trying to cram a whole novel's worth of plot into a single fortune cookie, just too much information in one place.
Information overload. So how did they solve that problem?
By teaching machines to do something humans do naturally, focus. That's where attention comes into play. And let me tell you, it was a total game changer for sequence-to-sequence modeling.
All right, break it down for me. What is attention in this context?
Okay, so think about how you read a sentence. You don't give equal weight to every single word, right? You naturally pay more attention to the important ones, the verb, the subject, maybe a descriptive adjective.
Totally. I'm definitely not analyzing every the and a with the same intensity.
Exactly. Attention mechanisms work in a similar way. They allow the model to focus on the most relevant parts of the input as it's generating the output.
Yeah.
No more relying solely on that single, potentially overloaded hidden state.
So it's like the model is highlighting the important parts of the sentence as it's reading, making sure it doesn't miss any crucial information.
You got it. This ability to selectively focus, it's a game changer. It means these models can handle much longer and more complex sequences than ever before.
This is already blowing my mind. But it gets even cooler, right? There's self-attention, where the model is basically, what, having a conversation with itself?
You're right, it does get even cooler. Self-attention takes things a step further. Now the model can attend not only to the input sequence, but also to different parts of its own output.
Hold on. So it's not just understanding the input, it's understanding its own thought process as it generates the output. That's wild.
It is. And this internal dialogue, this ability to make connections within its own output, that's what makes the model even more powerful.
Okay, this is blowing my mind a little. But, and there's always a but, this is where the order thing comes back to bite us, right? We can't have machines ignoring the concept of time.
You're catching on quickly. Here's the thing. Self-attention, for all its awesomeness, has a bit of a quirk. It gets so caught up in, like, finding connections that it sort of forgets. Well, the order things happened in.
Wait, seriously. We've taught this model to have complex internal dialogues, and now it's forgetting that sentences have a beginning, middle, and end.
It's not that it forgets entirely, but it doesn't place as much importance on the order. Imagine reading a poem where all the lines are jumbled up. You might still get some meaning, but the impact is lost, right?
That's a perfect way to put it. So how do we fix that? Can we just, like, hand the model a dictionary and say, learn your ABCs?
That's where positional encoding swoops in to save the day. And trust me, it's a pretty elegant solution. It's like we're giving each word in that jumbled poem, like a little tag. you know?
Okay.
A little reminder of where it belongs in the proper order.
Okay, now we're talking. Tell me more about these tags. What are they? How do they work?
Essentially, positional encoding, um, it injects information about each element's position in the sequence.
Okay.
It's a bit like giving every word a unique ID card based on its place in line.
Right.
This way, even when the model is busy making connections with self-attention, it still has a sense of the sequence's structure.
So it's still free to find all those patterns and relationships, but now it also knows that the cat sat on the mat hits differently than mat cat the sat on.
Yes.
It's about putting those puzzle pieces together in the right order.
Precisely. And here's the beauty of it. We're not talking about some, like, predefined system, right?
Okay.
We use mathematical functions, specifically sine and cosine waves, to create a unique representation for every single position in the sequence.
Hold on. Sine and cosine waves. Flashback to high school trigonometry. How does that work?
Think of it this way. Both sine and cosine waves have that, repeating up and down pattern, right?
Yeah.
But they're shifted from each other. That shift is what makes this whole thing tick. Shifted, you mean like one starts at the top of the wave and the other one starts halfway up?
You got it. And because of that shift, if you pick any point on those waves, the combination of its sine value and its cosine value is unique. No other point on those waves will have that exact same combination.
So it's like each spot on the waves gives us a unique coordinate, kind of like a GPS location, but for words in a sentence.
What a fantastic way to put it. And we can get even fancier. By combining multiple sine and cosine waves, each with a different frequency, we create even more complex and unique representations for each position.
Okay, different frequencies, different waves. Break that down for me like I'm back in high school.
Okay, so imagine a wave that goes up and down really fast. That's high frequency.
Okay.
Then picture one that takes its sweet time to complete a cycle. That's low frequency. By mixing high and low frequency waves, we get a huge range of unique values to work with.
It's like we're giving each of those word ID cards, like a bunch of extra digits.
Yes.
Making them super specific and informative. Exactly. And here's something else that's really neat about this.
Yeah.
The distance between any two positions, once they're encoded, stays the same.
Wait, really?
Yeah.
So if a word is in position 1 and another one's in position 3, that distance is always the same. Whether we're talking about a 10-word sentence or like a 1,000-word epic.
You got it. That's the magic of those sine and cosine waves and their carefully chosen frequencies. It's like we've created this consistent ruler for measuring distance within the sequence, no matter how much we zoom in or zoom out.
That is seriously cool. It's like we've invented a special map where no matter how much you zoom in or out, the distances between like landmarks always stay the same.
And that consistency is key for the model.
Yeah.
It makes learning patterns and relationships within sequences so much easier. This isn't just about teaching machines what information to learn. It's about teaching them how to learn it effectively.
This positional encoding, it's like the unsung hero of making sure AI doesn't lose track of time. It's the magic ingredient.
It really is. And it highlights something incredibly important about deep learning overall. We can't just throw data at a model and hope for the best, right?
Yeah.
It's about finding the smartest, most elegant way to represent that data, to give the model exactly what it needs to succeed.
So it's like we've got to speak the model's language.
Exactly. Think of it like teaching. A good teacher adjusts their methods for different students, right?
Right.
It's the same here. We need to adjust how we present information based on the model's strengths and weaknesses.
Makes total sense. Okay, so we've covered a ton of ground. Encoders, decoders, attention, and now this amazing positional encoding. But how does it all work together in the real world? Give me an example.
Let's go back to language translation.
Yeah.
A classic sequence-to-sequence task. Imagine you're translating a sentence from English to French.
Okay, so our input sequence is the English sentence, and the output we want is the French translation.
Exactly. Now, remember how we talked about those early models struggling with long, complex sentences? They just couldn't hold all the information effectively?
Right, like that overloaded fortune cookie. But now, with attention, the model can focus on different parts of the English sentence as it's creating the French translation. And thanks to positional encoding, we know those French words will actually be in the right order.
You've got it. It's not like this clunky word-for-word translation anymore. Now the model can understand the entire sentence's context, zeroing in on the words or phrases that are key to carrying the meaning across languages.
It's like we've taken a huge leap forward in how these models understand language, all thanks to these incredibly clever techniques.
Absolutely. And the best part is it's not just limited to language. These techniques are being applied everywhere. predicting stock market trends, generating music, you name it. Anything where order matters.
This is seriously cool stuff. Okay, one last thing before we get too carried away. You mentioned earlier that scaling the input data before adding positional encoding is important. Why is that? What does scaling even mean in this context? It sounds kind of technical. Is it as complicated as it sounds?
Not really. It's more about finding the right balance, really. Like,
Yeah.
imagine you're baking a cake and the recipe calls for like a teaspoon of salt and a kilogram of flour, right? You need both, but they're on totally different scales.
Okay.
If you're not careful, that salt could get completely lost in the mix.
Okay, I see where you're going with this. We don't want our positional encoding to get lost either.
Exactly. And often the data we're working with, think word embeddings or other pre-processed information, those values tend to be clustered around 0, relatively small.
So if our positional encoding is using these like bigger, bolder values, those smaller data points might not get the attention they deserve.
It'd be like trying to have a nuanced conversation at a rock concert. Those subtleties are going to get totally drowned out by the sheer volume of everything else.
Okay. So how do we turn down the volume, so to speak? How do we get everything on a similar scale so the model can hear it all clearly?
That's where scaling comes in. By scaling the input data, basically, like multiplying it by a carefully chosen factor, we can adjust its range to be more in line with the positional encoding.
Okay.
It's like adjusting the volume levels on each instrument so they blend beautifully in a song.
So we're not changing the meaning of the data, we're just making sure the model can, like, appreciate all the parts, including those important positional cues we've worked so hard to create.
Exactly. It all comes back to representation. How we present information to the model drastically impacts its ability to learn. And in this case, the right representation means making sure both the data and its position in the sequence get their fair share of the spotlight.
Makes sense. It's like fine-tuning the model's senses to make sure it's picking up on all the right signals. This is so much cooler than just like feeding data into a machine.
It really is. And just like fine-tuning an instrument can completely transform the sound of a piece of music, these subtle tweaks to how we represent data can unlock like huge performance improvements in our models.
It really highlights the complexity and like the elegance of this field.
Right.
We're not just dealing with cold hard code here. We're talking about the very nature of understanding, of how machines learn
Yeah.
and how we can best communicate with them.
We are. It's that fascinating intersection of technology and human understanding that makes this such an exciting field. We're constantly pushing the boundaries of what's possible, not just in terms of raw computing power, but in how we, comprehend the very concept of intelligence itself.
Yeah. It's like we're explorers charting a brand new frontier, but instead of maps and compasses, we're using sine waves and attention mechanisms. It's incredible to think where this journey might take us.
It really is. And while there's always more to explore, I think that's a great place to pause for today. We've covered a lot of ground, from those fundamental building blocks of sequence-to-sequence modeling, all the way to the intricate dance of positional encoding and how we can help our models make the most of it.
We have, and I think our listeners are now equipped to like drop some serious AI knowledge at their next tech meetup. But before we wrap up completely, I want to leave everyone with one final thought. We've seen firsthand how important it is to give our models information about the order of things, to teach them about like the flow of time in data. But what other hidden dimensions might we be overlooking? What other kinds of like secret information could we be encoding to help our AI companions grasp even more complex concepts? Something to ponder until our next deep dive. Thanks for joining us.
Always a pleasure.